In this video, we will show how the existence of electromagnetic waves follows from Maxwell's equations. Let's start with the graphical representation of electromagnetic waves. If the wave is sinusoidal with wavelength lambda and frequency f, then as we saw earlier, such a traveling wave can be written as, for the electric field, we can write E equals EY, that equals E naught, which is the maximum strength of the electric field, times cosine kx minus omega t. And then for magnetic field, B equals By, and that equals B naught, which is the maximum of the magnetic field strength, cosine kx minus omega t, where k equals 2 pi over lambda, omega equals 2 pi f, angular frequency, and we can write f lambda equals omega over k, and that equals the speed of the wave. Consider now a small rectangle in a plane of electric field. This rectangle has a finite height delta y and a tiny width dx. So this left arrow represents the electric field at point x at a certain time t, and the right one represents electric field at point x plus dx at the point in time t. Or I can rewrite this as E, and the right one would be E plus dE. Now let's apply Faraday's law to this rectangular loop. Faraday's law is the third equation in a Maxwell's equation, so which is integral over the closed loop E dot product dl should equal negative d magnetic flux, the first degree derivative of magnetic flux by t. First, we consider the left part of the equation for this rectangle that we have chosen, and along the short top and the bottom section of the length dx that we have, I am gonna highlight that short top and the bottom dx. Electric field is perpendicular to the dl. So when electric field is perpendicular to the dl, then we end up having the dot product dl equals 0. Just a reminder for you, let's recall that if you have two vectors, vector A dot product vector C, that equals AC cosine theta, and we know that cosine at 90 degrees equals 0. So therefore, because electric field and dl are perpendicular, so E dot product dl equals 0. Now along the vertical sides of our rectangle, I can write integral E dot product dl equals, along the right side it would be E plus dE delta y minus E delta Y, which will give me a dE times delta Y. For the right side of the Faraday's law, I can write d phi b dt equals the magnetic flux through the loop. So the magnetic flux would be dB dt times dx delta y. That's the loop. Since the area of the loop is dx times delta y, so this is the area of the loop. And since it is not changing also, so therefore I can combine these two and write the Faraday's law dE delta y equals negative dB dt dx delta y. From here, delta y's will cancel out. I will end up having dE dx equals dB dt. So let's not forget that E and B are functions of x and time. So we should write the partial derivatives in this case. So we will end up having dE dx partial derivative equals, oh, I forgot the negative sign in here. So negative the partial derivative of B. Let's call this equation 1 and take the derivative of the equation 1 by x. Then we will get d2e dx2 equals negative dB dt d2b dt dx. Let's call this one equation 2 and then leave this aside and then go back and see apply the same things for the magnetic field. So to find another important relationship between electric field and magnetic field, in the addition of our 1 and 2 equations that we found, we consider now a small rectangle in a plane of magnetic field whose length is delta z. So let's draw this. So we have this little triangle. We can consider that the length is delta z, and then of course the width would be again dx. To this rectangular loop, we apply Maxwell's fourth equation, integral closed loop B dot product dl equals mu naught epsilon naught d phi e dt. By the way, we originally we considered that there is no current, no charges, moving charges in the space, so it's a kind of a free space, empty space. That's why the fourth equation is written in this form. So again, along the short sides of dx, b dot product dl, let's just put the dx in here, would be equal 0 because the dx and the b are perpendicular to each other. So this is and then let's just call this left line vector as a b xt, and then the second one we will call bx plus dx t, or we can say b plus db. Okay, as we did in the case of electric field. Along the longer sides of the loop, our integral, okay, let's make it a little bit more visible. Integral dB dot product dl should equal b delta z minus b plus dB delta z, given that my the integration goes along the loop and this is the direction, like that. So which will give me a negative dB delta z. Let me just go back, and I feel like I forgot to mention you the direction of the loop for the electric field, where we had the loop going up in here and down here. Okay. Now, the right side of the equation, mu naught epsilon naught equals, mu naught epsilon naught d phi e dt can be written as mu naught epsilon naught dE dt over the loop, the electric flux over the loop, which is dx times delta z. Now, if we plug in our values into the original equation, equating these two expressions, we will get negative dB delta z equals mu naught epsilon naught dE dt dx delta z. So delta z's will cancel out, and I can get dB dx equals negative mu naught epsilon naught dE dt. Let's not forget those are partial derivatives, so I can rewrite it dB dx equals negative mu naught epsilon naught dE dt. I made a mistake, so it's should be the curly d dE dt, the partial derivative. Let's call this one our equation 3. And so let's take the derivative of this equation 3 by t now. Then I would have dB dx dt. I should have kept the negative on this side. Okay, I'm going to keep it in this side. Equals mu naught epsilon naught d2, oh, I forgot the 2 in here, d2e over dt2. So why I did this negative on the left side, because that is actually what I have on my equation 2. So if we go back to the equation 2, you can see this term with the negative in it is the same as this term right here. So therefore, I can actually substitute one with another one. So if I substitute negative d2b dx dt with the mu naught epsilon naught d2e dt squared in here. So I'm going to write plug in 3 into 2. Then I would end up having d2e dx2 equals mu naught epsilon naught d2e dt2. So let's double check if we did everything correct. Yes, that's the d2e dt2. Okay, well, does this remind you anything? Well, let's recall what is our wave equations. So usually our wave equation equals d2yxt dx2 equals 1 over v squared d2yxt dt2. So as you can compare these two equations, you will see that the our E satisfies, the function of E satisfies the wave equation. Therefore, from here, there's an interesting things come out. So I can say that this mu naught epsilon naught should equal to 1 over v squared. Well, let's write that down in here. So 1 over v squared equals epsilon naught mu naught, where the epsilon naught is a free space permittivity and mu naught is a free space permeability. From here, I can find the speed of electromagnetic wave equals 1 over square root of epsilon naught mu naught, which are the electromagnetic constants. Well, guess what? If I were you, I would stop right here, pause the video, and plug in the values into epsilon naught and mu naught and see what you get. Well, if you didn't stop, then I have to give it away. That is actually 3 times 10 to the 8 meters per second, which is the speed of light. So where our epsilon naught equals 8.85 times 10 to the negative 12 coulomb square per newtons times meter square, and mu naught equals 4 pi times 10 to the negative 7 Tesla times meters per amp. Now let's take a look at equation 1 and see what we can get out of that. So if we take the derivative of the sinusoidal function that we defined in the beginning, ddx of E naught, we had cosine kx minus omega t. Okay, let me put this as a square parenthesis. Then we will end up having this equals negative k E naught sine kx minus omega t. Well, let's do the same thing for the second part of this right part of the equations. dB dt equals d dt b naught cosine kx minus omega t. I again got confused with my square parentheses. So that will give me negative omega b naught sine kx minus omega t. Okay, so again the square parentheses here. Now let's plug this back into our equation 1. So this is to the left and this one is to the right. So I would have negative k E naught sine kx minus omega t equals that negative in front right here of dB dt. We have a plus here when we took the derivative. So it would be omega b naught sine kx minus omega t. So the signs will cancel out, and we'll see that E naught divided by B naught equals omega divided by k, which is in its turn equals the speed of the wave. or speed of the electromagnetic wave. So from here we can conclude that the speed equals E over B. Now let's go back to the equation 3. So equation 3, which was dB dx equals negative mu naught epsilon naught dE dt. So from here, if we take the derivative of dB by x, so that would be d dx b naught cosine kx minus omega t. This is the derivative by x. Previously we took the derivative by t, and so that will give us k times b naught sine and kx minus omega t, negative in front of it. And then the right side, if we take the dE by t, then we would have negative, oh, let me just write it for you guys. So that is a d dt E naught cosine kx minus omega t, which will equal negative negative omega E naught sine kx minus omega t. Okay, so x in here, k in here. Now let's make them equal to each other. So we will have negative k b naught sine kx minus omega t equals negative mu naught epsilon naught omega E naught sine kx minus omega t. So the signs will cancel out. We will end up having b naught over E naught equals mu naught epsilon naught omega over k. And so let's recall what is omega over k. This omega, oops, I wrote epsilon, it should be omega. So this will give us, this is the velocity, right, the speed. So we have a mu naught epsilon naught v. So from here, from the previous one, we know that E over B equals V, so I can say B naught over E naught equals 1 over V. That equals mu naught epsilon naught V. So this guy is 1 over V. We derived from the equation 2 right here. So from here I could say 1 over mu naught epsilon naught equals V squared, or I could say V equals 1 over mu naught epsilon naught under the square root. Well, we end up getting the same result. So this is the second way of finding the speed of electromagnetic wave. Thanks for watching. Stay tuned for more videos.